Lewis structures. Let's talk about them. Lewis structures show the distribution of outer valence electrons in an atom, molecule, or polyatomic ion. So just to review, unshared electrons are shown as dots. So example is carbon. Carbon has 4 valence electrons, so we just put them around. 1, 2, 3, 4. Notice how we're just going in a clockwise direction, 1 on each side. Let's say that we have a molecule such as fluorine. So fluorine has 7 valence electrons total. Notice how right here, these 2 electrons in the middle can form a bond, and a bond is represented as a straight line. So when we draw out fluorine as a molecule, as F2, we draw it with this lovely bond right here. So this bond represents 2 electrons. Every time you see a bond, it means that you're sharing those electrons between 2 atoms instead of just the one. Now let's remind ourselves about valence electrons. Valence electrons, the easiest way to remember how to do them is to notice their group number. So group 1 has 1 valence electron. Group 2 has 2. 3 through 12, these are your transition metals. These vary. And so we're not really going to worry about those. Groups 13 through 18, all you have to do is take off the 1. So there's 3 in group 13, 4 in group 14, and so on. When you get to group 18, from neon down, there's 8. However, helium only has 2 valence electrons. So just kind of keep that in mind when you're doing these problems. Okay, let's go over the rules for writing Lewis structures. The first thing you're going to do is count the number of valence electrons available. If you have a polyatomic ion and there's a negative charge, you're going to add electrons to your total. Because remember, negative means electrons because they're negative. If you have a positive charge, you're going to subtract the electrons. Then what you're going to do is draw a skeleton structure using single bonds. So our most common types of skeletal structures that we're going to use for this class have 5 atoms or less. So for example, if we were to draw out these Lewis structures, we'd have an atom in the center, and then we would have atoms all around it. So notice how we have the central atom, that's the X, and then terminal atoms, which are the lowercase a. So our structures are all going to look something like that when we have 5 or fewer atoms. A couple of things that will be helpful is that the central atom, which is this X right here, is usually written first in the formula. So that's how you know it goes in the middle. But it's also usually the least electronegative atom in your compound. Terminal atoms, which mean outside, these are being represented by the lowercase a right there in our structure. And terminal atoms are usually going to be hydrogen, oxygens, or halogens. And remember that halogens are your group 17 on the periodic table, or 7a. And then another thing that's helpful is that halogens and hydrogens can only have single bonds. So halogens already have 7 valence electrons. They only need 1 more to have a full octet to make them very stable. And hydrogen only wants to have 2 valence electrons because the first energy level only has 2 electrons, which makes hydrogen very stable. So therefore, they can only have single bonds. Okay. Then after that, every time we see a single bond, we're going to deduct 2 electrons every time we see a single bond. And that's going to help us keep track of how many valence electrons we've used. Then after we do that, we're going to distribute the remaining electrons so that each atom, if possible, can have 8 electrons around it. Now, notice these words, if possible. Sometimes it's not possible. So keep that in mind. Also remember that hydrogen and helium only ever want to have 2. They don't want any more than 2 because 2 makes them very, very stable. Okay, let's practice. This first molecule is called hydrosulfuric acid. Hydrogen has 1 valence electron, but notice how there are 2 right here. So what we're going to do is we're going to put 2 times the 1 valence electron, then add that to sulfur's valence electrons, which are 6. So now we get 2 plus 6, which is 8 valence electrons. Okay, usually hydrogen is written first. It's the central atom. But hydrogen doesn't ever want to be the central atom because then it will have 4 electrons automatically around it. So in this case, we're going to put sulfur in the middle and hydrogen's out to the side. Usually we put things horizontal and then go down and then go up when we're making our Lewis structures. So now what we're going to do is we're going to subtract 2 electrons from each of these bonds. 2, 4, and we're going to subtract it from 8 because we want to keep this 8. We want to make sure we use all of these 8 valence electrons so we know where they are. Now what we're going to do is compare each atom and see where we need to have more electrons. So right here, this hydrogen has 2 electrons, and that's all it wants. So this is good. The hydrogen on the right, it has 2 electrons as well that it's sharing. That's all it wants. It's good. Sulfur, however, only has 4 electrons around it, but it wants 8. So we're going to put these 4 electrons that are left over around our sulfur, and notice how I'm putting them in pairs. We don't do that in just with one atom, but when we have a molecule or a polyatomic ion, we do, because again, it makes our life a lot easier. So now let's double check. Left hydrogen still has 2. The right hydrogen still has 2 valence electrons. This sulfur now has 2, 4, 6, 8, which is what it wants. And now have we used the total of 8? So if we have anything higher or less than 8, then we know we have to relook at our structure. So right here we have 2, 4, 6, 8. That means it's good. So if I'm going to write this over again so it looks better, this is what our Lewis structure for hydrosulfuric acid would look like. Let's do another example. Let's do ammonium. Okay, first, again, we're going to count our valence electrons. So nitrogen has 5. Hydrogen, there's 4 atoms of hydrogen, but each has 1 valence electron. Now notice we have this positive sign. Okay, the positive sign, remember, means that we're going to subtract 1 electron from the total. So I'm going to put -1 up here. So 5 plus 4 is 9, -1 equals 8. So we have 8 valence electrons. Now the first element written here is nitrogen. It's not a hydrogen, so we can put it in the middle. And the hydrogens are going to go all around it. And notice there's 4. So I'm going to put the hydrogen on each side of that nitrogen. Then I'm going to count how many single bonds we have. We've got 1, 2, 3, 4. Each represent 2 electrons. So that means we've got 8. So we're going to subtract 8 from up here. So 8 minus 8. We have no valence electrons left. So let's make sure that every single atom has what it needs. Okay, this hydrogen here, it has 2. The bottom hydrogen has 2. The right hydrogen has 2. And the top hydrogen has 2. So all the hydrogens have what they want. Now let's check our nitrogen. Our nitrogen has 2, 4, 6, 8. It has what it wants, and we've only used a total of 8, which means that we have done well. So now we're going to just rewrite it again without all the circles. Now there's one more thing we need to do, and that's because of our charge right here. Okay, whenever we have a charge, we have to show it. So what we're going to do, let's erase that so it looks a little bit better. So we're going to put brackets around this entire structure. And then on the upper right hand side, we're going to put the charge that is on our formula right there, so that anyone who looks at this will say, oh, well, now we know why there's only 8 valence electrons showing in this structure instead of 9, because we have a positive charge. Okay, let's look at a different scenario. Let's say that we don't have enough electrons. In this case, we're going to form multiple bonds. So there's 2 different types of multiple bonds. There's the double bond, which if you notice there's 2 lines, so that means we're going to have 4 electrons that are represented. And then there's the triple bond. Notice 3 lines, so you're going to have 6 electrons with the triple bond. Okay, so let's look at the first one. We're going to do this exactly the same way as we have the ones before. So nitrate, we need to have a formula, and it's a polyatomic ion, so when we look at that one, the formula is going to be NO3 with a -1 charge. Let's add up the number of valence electrons. Nitrogen has 5, oxygen has 6 valence electrons each, but there's 3 of them, so we're going to times that by 6. And now in this one we have a +1 charge. Sorry, a -1 charge, which means we're going to add 1 to our total. So we have 5 plus 18 plus 1 makes 24 valence electrons. Okay, so again, remember that negative charge means we're going to add an electron. So nitrogen is first, so we're going to go ahead and put that in the middle. We're going to put our oxygen around. Those are our terminal atoms. Now we're going to add up how many electrons we've used. We've used 2, 4, 6. So 6 minus 24 is 18. Okay, now at this point in time, a trick that I like to use is I like to make all the terminal atoms have 8 valence electrons first. And the reason why is because the terminal atoms are usually more electronegative, which means there's a greater electrons are attracted to them more than they are attracted to others. So it would only make sense that those are more electron dense. And I'm going to put these around on in pairs again. So we have 2, 4, 6. I'm going to stop there because this means there's 8. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, now I'm stopping because I've used all 18 now. So now we've used all 24 valence electrons. So now let's go ahead and look to see what's going on with each atom. So this oxygen, it has 2, 4, 6, 8. That's good. Bottom oxygen, 2, 4, 6, 8. That's good. The right oxygen, 2, 4, 6, 8. That's good. The nitrogen, however, if you're noticing this, only has 6. That's not good. So what we can do is we can form a multiple bond. So we're going to take an electron from any of these terminal atoms. Doesn't matter which one. Let's say this one, for example. And we're just going to move those electrons to a different location. We're going to move them in between the nitrogen and the oxygen. So when we rewrite this, we're going to have the single bonds on the horizontal, and then down below we're going to have a double bond. And then we're just going to fill in the corresponding electrons. So we've got 3 pairs around that oxygen, on the left oxygen. Now we only have 2 pairs on this oxygen down below, and on the right oxygen we still have the 3 pairs. Okay, let's double check. This oxygen still has 8. The bottom one has 8. The right one has 8. And now if you notice, the nitrogen has 2, 4, 6, 8. And that's perfect. And then we've only used the 24. Let's double check. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we're fantastic because we have a charge. We put our brackets around this with the charge on the upper right hand side. Okay, let's go ahead and do cyanide. So cyanide is another polyatomic ion. Its formula is Cn with a -1 charge. So let's add up our valence electrons. Carbon has 4, nitrogen has 5, and this -1 means we're going to add an electron. So we get a total of 10 valence electrons. Okay, here we only have 2 atoms, so we don't have a central atom per se. So we're going to go ahead and just do them horizontal. We've used 2 electrons right there, so we're going to subtract 2 from our total of 10. We have 8 left. On this one, it doesn't really matter which one you start with. If you want to be really specific, you would start with the nitrogen because it's more electronegative. But again, it's okay if you don't. So, but let's go ahead and do 2, 4, 6, 8. And that's because I have the 8 left down there. So now I have no valence electrons left to use. Now let's check to see what's going on with our atoms. Here's this carbon. It has 2, 4. The nitrogen has 2, 4, 6, 8. So the carbon doesn't have